We're starting 7.3. I decided that I think I'll start trying to record these without the whiteboard because when I was teaching the class this last time on Tuesday, it went pretty well with just me showing you the screen. So I'm going to try that now. This is just my quick greeting at the start. So hello, and now I'm going to say goodbye from my video. Okay, let's go. We're on 7.3. I'm talking a little quietly because it's kind of late right now, but I think the recording will pick up all right. If not, then complain and then I'll record it in the daytime. Okay, so 7.3, this is hypothesis testing for the mean, mu, when sigma is unknown. This is analogous to section 6.3. If you think back to section 6.3, that was when we did the t-distribution, right? Because we didn't know sigma, but we knew s. S is the sample standard deviation. Okay, same setup as before. First of all, we have to check that we have a normal distribution. So we want to make sure that n is bigger than or equal to 30, or else that we know the overall population is normally distributed. One of those two things. Now, once we check those two things, this is sort of the flow chart. If sigma is known, then we use the z-score. That's back in 7.2. And if it's unknown, then we'll use the t-score instead, and the t-distribution. It's basically going to be kind of like the way we tackled 6.3 with the t-distribution instead of the normal distribution. All right, once we can assume the sample mean is normally distributed, if the population standard deviation sigma is known, we use the z-score. This is just repeating what I just said, this paragraph right here. If the population standard deviation is unknown, then we use the t-score instead, with the degrees of freedom df equals to n minus 1. That's just like before as well in 6.3, right? Remember that? The degrees of freedom, we just take the size of the sample and subtract 1. Okay, so what's that going to look like in practice? So here's the first question. Assume the population is normally distributed. Decide whether or not to reject H naught given the significance level alpha. This is pretty much like what we did in chapter 7.2. Now the only difference is we're going to first calculate the t distribution. Okay, I should actually add that in somewhere here. So let me add that in right over here. So do you remember? Think back with me. Actually, I'm gonna do it on the right side. I have a math editor that I like to use when I'm trying to write things quickly. So this one is called Lix. I'm gonna write my math on this side. So recall with me, we had this equation, right? How do we find the z-score? Remember the z sub x bar? That was equal to, it's the sample mean and subtracted by the true mean, or our estimate of it at least, and divided by the standard deviation for the means. Yeah, this is the calculation that we had. And you remember this? This is from the previous section. And then we said, okay, well, actually sigma sub x bar, that's really just equal to sigma over the square root of n, yeah, that fraction. Well, for the t-score, the t value, it's actually pretty much the same thing. It's t sub x bar to denote that it's a t-score for this sample mean. And what is the fraction? It's probably what you expect it to be. It's that same x bar. We're also subtracting mu again. The only thing that's changing is, since we don't know the overall standard deviation, we're just going to replace that with the standard deviation that we do know. So that's the s. Remember, s is the standard deviation for the sample. So we don't know the overall population standard deviation, but we do know the sample standard deviation, and so we can calculate that with s instead. That's actually, really, if you think about it, this is an approximation for the true standard deviation here. Okay, let's move on. Now, where were we? Okay, so that means I should really include that equation here, though, as a note to myself. So t, it's going to take me a little longer to type it in this format for Word, but not so bad, I guess. Whereas a lot of peculiarities when you're trying to type in equations. What was it? It's bar x minus mu That's over, we don't know sigma, so it's S divided by square root of n, like that. Yeah. This square root doesn't look right. It should be, I don't know how to make it look right. It's the square root of n. But this is the one here. I just recopied this same equation. Yeah, so you should make a note of this. That's how we calculate the t-score. Okay, so let's look at what we're given here. In this question, we're given the claim mu is equal to 15. Okay, so that will be like our h naught. What I'm going to do is I'm going to use this right-hand side for my equation editor. So I'm going to just shift this slightly over and just use this as my notepad here. Just kind of ignore these lines. This is kind of a peculiarity that this particular equation processor has. It's not really equation processor, it's really a type of text, I guess, text and equation processor. Anyways, what do I want? I want h naught. So h naught, first of all, is the claim that mu is equal to 15. Remember, h naught is a hypothesis that includes the equality. So the alternative hypothesis then is that mu is not equal to 15, right? The complement of the original h naught. Okay, so now that I have that, what else do I need? So I have alpha equal to 0.01, that's nice. S is equal to 3.23, the sample standard deviation. We have the sample mean x bar, and we have n equal to 36. So what I do need to know, and I don't know yet, is the t-score. So I need to figure that out. I'm going to use that formula I typed in right over here. And t sub x bar is going to be equal to, I'm going to plug in the numbers, 13.9 minus 15. So my sample turned out to be lower, right? Kind of significantly, but let's see. We'll see if that's going to be far enough away that we can reject or not. Yeah, let's see. And then the bottom is S, so 3.23 divided by the square root of n, which is the square root of 36. Okay, I'm going to just take a moment to plug this into my calculator and see what I get. Okay, remember when you're doing these things, I want to keep the numerator in its own set of parentheses, or else press enter once before you finish the calculation. And same thing for the denominator. You want to think of writing this thing in its own set of parentheses so that you preserve the correct order of operations. Okay, so I have negative 1.1 on the top divided by the square root of parentheses, 3.23, divided by square root of 36. Which I could just put 6 if I wanted to. Or that's negative 2.0433. Blah, blah, blah. I think it's 2.0433. That's enough digits for us. Okay, from this point on, we're going to approach the question very similarly to how we approached it in the previous section. The only difference now is that we're going to calculate the t-score using the t-distribution instead of the normal distribution. So how do we do that? Well, we do the same thing like back in section 6.3. We take the t... Oh, did we do this? Actually, I'm not sure if we did this or not. But it's the t-CDF, which is the equivalent of the norm CDF. You'll find that in the same place of your other distributions. So t-CDF, that stands for the t-score cumulative distribution function. And what I'm going to put is the lower bound, which is, I'm doing a two-tailed test this time, right? Because HA is not equal. That means I'm doing both sides. So actually double, 2 times TCDF of, this here is a negative score, so I'm looking at the left-hand side. I'm going to calculate in terms of the left tail. So negative 10,000, negative 2.0433, comma, oh, this time instead of comma 0, comma 1, because I'm using a t distribution, the last space is for the degrees of freedom. This tells us roughly how much information we have. So, okay. The next line here went a little too big. There we go. Okay, so here what I'm going to do is just enter that into my calculator and see what I get. And let's see what I get. That should be equal to. Times by 2. 0.0486, blah, blah, blah. All right, this is the p-value that I just calculated. This is the p-value. It's equal to this thing. 2, because this is a double-tailed test, two-tailed test. The t-distribution function from the left to the point that I pick. Negative 10,000 to the point that I pick. And then 35 is the degrees of freedom. And I get 0.0486. Well, now we've got to compare that to our alpha value, 0.01. Well, this is bigger than 0.01. So do you remember what that meant? That meant that we failed to reject H naught. Okay, so this is the answer for problem number 1. Okay, let's move on to problem number 2. Same idea. I'm gonna erase some of this stuff. Okay, let's just alter it a little bit. Okay, so this time we have a claim of mu is greater than 25. Well, that would be the alternative because that's the part that has no equality, right? So that means the original null hypothesis would be less than or equal to 25. Okay, which one is the claim? By the way, did it ask about the claim? It did not ask about the claim. Okay. I guess I could answer it though. Just real quick, coming back to the first question, the claim was that it's equal to. That was the null hypothesis, but we failed to reject that null hypothesis, which means that this might be true. The claim might have been true, right? We haven't rejected that hypothesis. Okay, now moving on to number 2. So the claim this time is this alternative hypothesis. I like to just make a note for myself that this is the claim. And this also means that it's a right-tailed test because the alternative hypothesis is pointing to the right, yeah? Okay, let's see. Again, just like last time, I have all the information except for the t-score, t-value. So I'm going to fill in my values to get that. T-score should be, this time, 26.2 minus, what is the mean? The claimed mean is 25. So we're assuming, again, when we do these hypothesis tests, we're assuming to begin with that H naught is true. So we're assuming that the mean is less than or equal to 25, and we're using 25 as our working value for the mean. Okay, so 26.2 minus 25 divided by the standard deviation is 2.32 divided by the square root of n, 17. Okay, let's see what this gives us. Not going to be that number. This actually should be positive because it's to the right. 26.2 minus 25 is 1.2 divided by parentheses 2.32 divided by the square root of 17. All right, and I get 2.1326 unless I entered something wrong. And if I did, then please let me know so I can correct it for everyone else. Okay, this time we're not doing a double tail test, so I don't need a 2. I'm doing a right tail test because if the alternative hypothesis is greater than. So I'm going to use the right side. This is my lower bound now, right? From this point onwards, so I'm checking. So I'm going to do a TCDF. That is the lower bound, 2.1326 up to 10,000. Or I put 100,000, but no harm in that. And then I want the degrees of freedom, which is 16, 1 less than n. Let's see what this gives me. Okay, so I'm punching it into my calculator. This is 2.1326, comma 10,000 or 100,000. Why not? And then comma 16, and I get 0.024, and that's enough because I just need to compare it to 0.05. Well, this guy is less than 0.05. Let's write this in the next line here with some spacing. Okay, so 0.024 is less than 0.05. That means this time I reject H naught. Reject H naught. So this is the answer for number 2. Okay, the p-value is less than 0.05. My allowable, or I'm sorry, my significance level. It's less than the significance level, so it means it's pretty unlikely it's going to happen that this is going to be the mean, 26.2, given that this was true. All right, that's number 2. Let's move on. I'm going to just modify this again. So let's kind of leave some of this stuff. So I don't have to type everything all over. Okay, so this time, okay, claim is that its mu is not equal again. So we're again using a two-tailed test. The not equal part, that is the alternative hypothesis, 52,200. Okay, what's this top part? This should be equal to something, 52,200, right? Alpha is 0.05, S is 2,700, so this is going to be down here, 2,700. And then on the top, the mean is 53,200 minus that assumed mean of 52,200. And the bottom, n is 34, so we have the square root of 34. Okay, let's see what this gives us. You know, for these ones, for these guys, I remember in the previous section I showed you a way around finding the z-score, but I don't really know of a similar analogous method for the t distribution, because we don't have that option when we're doing the TCDF, right? It's already kind of normalized, so we need to find the actual t value first. All right, this is 53,200 minus 52,200. Oh, that's pretty obvious. That's 1,000. Okay, divided by, in parentheses, 2,700 divided by the square root of 34. And that gives me 2.1596. Blah, blah, blah. All right, and this time we're doing a two-tailed test, right? Because H alternative is not equal. By the way, that was the claim, so I'd like to make a note of that. Claim 1 is not equal, so the p-value is going to be 2 times one of the sides. And since I have the positive value, I'm going to work to the right. 1, 2, 3, 4, 5. That's fine. 10,000. 2.1596, comma 10,000, comma, and then the degrees of freedom, which is 33 this time. 34 is n. 1 less is 33. All right. What does that give me? Let's see. So second vars for distributions, I want 2 times the TCDF of 2.1596, comma 10,000, or 100,000, comma 33. And it looks like, almost forgot to multiply by 2. Multiply by 2, that's 0.038. That's enough to compare to 0.05. It's less than 0.05. Yeah. So less than that means it's a rejection. Reject H naught. Now in terms of the claim, what does that mean? It means that we accept the claim. We accept the alternative hypothesis, which is the claim. Yeah, so that means we accept the fact, the fact that the true mean differs from the estimated mean. The mean is not 52,200, in other words. Yeah, okay, cool. Let's see, how much more we got here? We got, I think, just 2 more questions, and we're done. 2 more questions, that's it. Next ones are word problems, but really the process is going to be the same. Okay, let me just work from a clean slate here, clean board. All right, used car dealer says that the mean price of a 3-year-old BMW sedan is over $20,000. Okay, right here, let's start right away writing down our claim. So the claim is that, let's write this first. So we have H naught, and we have this alternative HA. The claim is that the price, the mean price, is over $20,000. So they're probably telling you this as the car dealership because they want to charge you over that, right? They want to charge you more than the mean, or they want to charge you a high value, right? Okay, so the original then, the H naught hypothesis, that would be that mu is less than or equal to 20,000. This is what you think, right? So the claim though was this guy. That thing. Sorry, my spacing is weird. You know, the way this word processor works. It's not really meant for primarily word processing. So spaces have this little funny symbol here, but just ignore those. Okay, so that's a claim, and then what else do we need to know? Let's just write our facts down. We know that a random sample is taken of 22. Okay. Interesting. Okay, so actually this is n equals 22, blah, blah, blah. If you look at this, there's nowhere in the question that it says we have a standard distribution. So actually I kind of skipped that step, and n is only 22. So in fact, this is kind of a wash, this question. This is the true answer. There's no math to be done, since we don't know if the data has a standard distribution, or has a normal distribution. So actually, in a real world situation, we could just stop at this point. However, that being said, I would suspect that the prices of a car would have a normal distribution. So even though it doesn't say it, let's just do the math just for the practice of it. Okay, so but if you had said this like on a test, I would accept this as an answer because there's no indication here that it's normally distributed and n is not bigger than or equal to 30. Okay, so let's come back. Let me just see if I can recover what I had written though, just so we practice. Okay? All right, so n is equal to 22. That means our degrees of freedom is equal to 21. What else do we know? We know, what else do we know? Yeah, we know that the mean price of those 22 cars is 19,840. So that means X bar, in other words, is 19,840. Right? Okay, sweet. What else do we know? Standard deviation of that sample that we have is 190. So that means S is 190, not sigma S, because this is for the sample only, right? Okay, we also know alpha. We know alpha. I'm going to put alpha up at the top. This is kind of like a big overarching idea. We're not going to use that to the end. Alpha 0.05. All right, so this is all the information gathered. If you look at this setup we have here, this is now kind of pretty much like one of these questions, right? We just kind of did a little bit of interpretation, reading the question, and now it's set up to do. All right, let's see. First thing we need to calculate is what is our t sub x bar square. So that's going to be equal to, first of all, our value, 19,840, minus the supposed mean, 20,000, all over the standard deviation, 190, divided by the square root of, divided by the square root of the size of the sample. So divide by square root of n, which is 22. All right, let's punch this thing in and see what we get. 19,840 minus 20,000 is equal to negative 160 divided by, in parentheses, 190 divided by the square root of 22. Okay, oh, interesting. That gives me negative 3.9498. So already, just looking at this value, I pretty much know what's going to happen. This is a really large left number, right? Large meaning like 3. Oh, it's almost 4. It's almost 4. Not exactly standard deviation, but yeah, standard deviations from the mean to the left. So that means it's pretty likely that this null hypothesis is going to be true. We're going to accept it probably, or at least fail to reject. Okay, let's see. So we're going to calculate the p value, but we're using a right-handed test. Right-handed test. Interesting. Yeah, this part is kind of interesting to me. This might throw you off a bit because if you look here, we have a negative t value, right? Negative t value. But the claim is that it's bigger. So what's going to look like is when we plug in our bounds, it's going to look like this. We're going to do a right-handed test. So it's t CDF with the lower bound is going to be negative. Well, we're going to the right, yeah. So negative 3.9498. And we're going up to 10,000. And then we're going the degrees of freedom, which is 21. Okay, so let's see what this is. TCF negative 3.9498, comma 10,000, comma 21. I think I put 100,000 again, but that's not a big deal. Okay, this is 0.99963. Okay, so what does this mean? Think about this value, what this is indicating. We have an extremely high probability this time, right? Extremely high probability. So this time we're looking at we're assuming that H naught was true. We're assuming that the mean is less than or equal to 20,000, because when we do these hypothesis tests, we always start by assuming the null hypothesis to be true, right? So we're assuming the null hypothesis to be true, that it's less than 20,000. So if it's less than or equal to 20,000, what's the probability that I end up with something that's less? Well, that seems pretty likely to happen, right? In fact, it's very likely to happen, 0.999633. So this is the value that I'm comparing now to my alpha value. This is way above 0.05, right? And remember, when something is bigger than the alpha value, that means that we fail to reject H naught. We fail to reject the null hypothesis. So when we say fail to reject, really what we want to be thinking is we're essentially accepting. Essentially we're accepting, right? Which means the opposite for H naught, which means we essentially reject the alternative. Yeah? So interpretation now, what does that mean? We essentially reject HA. That means there's not enough evidence to support the claim. The claim was HA, right? There's not enough evidence to support that claim. Sorry, let me just split these guys up into the next line. Let's try to fit everything in one page. Let's shrink it down a little bit. So there's not enough evidence to support the claim that the mean is over 20,000. Okay, I'm gonna pause here.